Hey everyone, welcome back, and today we're going to be doing something a little different. It's just a quick short video, kind of doing a quick word problem that I see come up on a lot of different math Olympiads or math-related competitions, where we're transforming word problems and given information in these sentences and word problems and formulating them into actual expressions and or equations to then be able to actually algebraically solve from there, right? And a very, classic structure for word problems, a very classic word problem that I want to talk about and discuss in today's video is, very straightforward two-digit algebraic, kind of number word problem, right? And just to kind of quickly type it out here, I'll have a text box somewhere right here. And basically the way the problem is worded is we are given that a two-digit number has the property, okay, it looks like I really just can't spell today, that the sum of its digits is 11. We're also given that if we reverse, or if you reverse, if you will, the digits of that number, the new number is 27 more or greater than the initial number prior to when we actually reversed it. And it basically just asks us what that number actually is, and I'll keep this text box here just for reference as we actually begin to solve the problem. And let me also increase the size of this. I think that way it'll help as well. Right? I don't know if there's a way we can, okay. I'll make that like something like 60, right? Cool. That is the problem statement here, right? And effectively, we have to think of how we can really solve this problem. Obviously, one method we could do this is just the straightforward guess and check method. And one reason why this actually wouldn't be too bad of a solution, relatively at least, for this problem, is that we're given that this is actually a two-digit number. And for that reason, we know that there's only, a very finite, limited possible number of numbers that this could be, because we only have two-digit numbers to go from 10 through 99. That isn't even many numbers. In fact, that's only, I believe, 80 numbers, right? Rather, not 80, but 99 minus 10 plus 1, or 89 plus 1, or 90 total numbers, right? Which is, not that bad. 90 numbers isn't a lot in a range to cover. We could definitely try to guess and check for all the values that have some digits to be 11. But there's actually a smarter way to solve this and a more scalable approach as well that would also work for larger, input sizes and for larger numbers, and that is the actual algebraic method. And the way this algebraic method is going to be formulated is we have to actually create equations based on the given information from this problem to then solve for those missing variables and get our final resulting integer, right? Now, let's assume that the two-digit number that we're initially or originally given is xy. Now, effectively, this does not represent x times y. That's not what this expression is really signifying, but rather that we're given, or rather that this initial or original two-digit number is in the form of xy, meaning that the first or tens digit is going to be x, and the ones or unit digit in this two-digit number is going to be y. So for example, if we had the two-digit number 27, x would be equal to 2, and y would be equal to 7. This does not signify 2 times 7 or x times y, but rather just 2 and a 7, kind of being concatenated into each other to one integer or to form a two-digit number of 27. That's the whole point of this xy. And the key thing is here that x is our tens digit and y is our unit digit, right? So that's quite straightforward. Now, if xy in this format is our two-digit number, that initial or the original one, well then we know that based on the first property of this two-digit number, that x plus y has to be equal to 11. And we know this because we know that x and y are our two digits in this two-digit number, and we know that the sum of the digits have to be equal to 11. And if the sum of our digits is the sum of x and y, well then we know that x and y, or x plus y's sum, has to be equal to 11, and hence why we have this initial expression here. But notice how we're given, or rather that we formulated two unique variables, right? And whenever we have two unique variables, we need at least two unique equations to be able to solve from them. So we very simply, got our first equation that x plus y, or the sum of our two digits in this two-digit number, have to be equal to 11. And the trickier part is to form that second equation to get enough information to actually solve for our x and y to get our initial input integer. Now, how can we decide to do that? Well, to kind of reiterate what the second property of this two-digit number was in the word problem itself, it says that if we reverse the digits of the original number, we know that it'd be 27 greater. And it looks like I just completely forgot to type that, so let me go back and type it. Right? And I forgot to type that quick property. So the property was, if we reverse the digits, the new number, so, okay, looks like my cursor probably wasn't working when I was doing that. The new number formed is 27 more than the original number, right? So if we reverse the digits, the new number formed is 27 more of the original number. Okay, never mind. So I did have that. That's very odd. Number formed is 27 more than the original number. Perfect, right? That's kind of just a quick summary of that problem. That's cool, right? We like that. Nothing, very unique about that. Now, we understand that, okay, cool, if we reverse the digits of x, y, our resulting kind of value is 27 greater than our initial value. Okay, so what can we really do about that? Well, again, let's go back to our initial kind of instantiated input, and that is xy. We said that xy was that original, I'll just type OG here, two-digit number. So if that is the case, how do we reverse the digits of x, y? How can that really, logically work? Well, the way that would work is we go from x, y, reversing that, to y, x. Now, it isn't as simple of just saying, well, okay, isn't xy just equal to yx? Well, no, because that would signify that x times y is equal to y times x, and so when we solve for x and y to get our initial variable, we'd have, rather incorrect formed equations. And now, this is where we use the property of two-digit numbers and just the property of actual integers to solve for this second equation. When we have a two-digit number that has digits, or, digits x and y, that means that x is our tens digit. X is going to be our tens digit, right? And that means that y is going to be our ones digit, right? And again, going back to that initial example that I was talking about, if we had the two-digit number 27, x would be 2 and y would be 7. This isn't 2 times 7 or 2 plus 7. This is 27. Now, this 2 actually has a value of 20, and the reason why is because it's actually in the tens digit position or tens digit index. And so rather, this is going to be 2 times the tens digit value plus 7 times the ones digit value, right? Which would then give us 20 plus 7, or 27. So going back to our, general approach or form of this two-digit integer, if we have xy to be our initial or original two-digit number, we know that this has a value of 10 times x, because x is our tens digit, plus y times 1, because y is our units digit. Now, really, this simplifies to 10x plus y, because anything times 1 is just that value itself. This represents the value itself of our initial input integer. Right? This is just a form, or rather format, of the input two-digit integer, or the original two-digit integer, and this is the actual value of it. Now, we know that the value of our original two-digit integer is going to be 27 less than the value of our reversed two-digit integer. Now, we know that the reversed two-digit integer is, instead of xy, yx. We're simply reversing the position or indexing of these two elements. Now, again, using the same logic of our tens digit value and our units digit value, what is the actual value of yx? Well, it would be 10 times y plus 1 times x, or x times 1, or 10y plus x. Right, so we know that 10x plus y, the actual value numerically of our original two-digit integer, plus that extra 27, would then be equal to the value of our reversed two-digit integer, 10y plus x. And from here, believe it or not, we actually do have everything we need to solve for x and y, and to kind of just consolidate what we just discussed, going a little, okay, let me, on a different page here, we see that x plus y, again, the sum of our two digits was 11, and 10y, let me rephrase that, 10x plus y plus 27 is equal to 10y plus x. And again, we simply got that from actually reversing the digits and simulating those different operations, again, as we saw right here. Right, 10x plus y plus that extra 27 would then equal the value numerically of our reversed two-digit integer. Now that we actually have those two equations, we can very simply just use all that information to then solve for x and y, because as you can very clearly see here, we now have two equations for two unique variables, right? And that's a very straightforward process to solve. We can solve this using elimination or substitution. But first, let's actually simplify this second equation. Doing that, we see that 10x plus 27 is equal to 9y plus x. Or 9y is equal to 9x plus 27. Dividing both sides by 9, we see that y is equal to x plus 3. Now that we've got y in terms of x, let's plug in that y in terms of x into the first equation. And doing that, we see that x plus 3 is equal to 11. Combining like terms and simplifying the equation on both sides, we see that 2x is equal to 8, or x is equal to 4. And so if x is equal to 4, well then y would equal 11 minus 4, or y would equal 7, and voila, we've got the two digits values themselves, and from there we can very easily just plug that back in and formulate our actual original two-digit integer. Recall that our two-digit integer originally was xy, and so that would simply just be 47 or 47. And we can also verify that because 4 plus 7, the sum of its two digits, is indeed 11, and 47 plus 27 is equal to its reversed form, or 74. Both of these conditions are held true. And so that's how you very simply solve this problem, using algebraic and rather formulaic conversions to actual algebraic equations, and simply solving for unknown variables using the given information from the context of the problem. So if you guys enjoyed this video and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.